Yes, hello folks. I'm going to go over some of the material that will be important for your second exam, that is from chapters 4 to 6. I have listed these topics, and if you have the fundamental information about these topics, then you're good. So let me go over these one by one just to remind you about them. All right, so we started off that chapter mainly with pressure. Okay, pressure is caused by what? So generally pressure is force over area. So if there is a force offered on a certain area, like if a book is sitting on a table, the book's weight is pushing on the table, and therefore there is a force, and there is a certain area. How concentrated the force is, that is what is measured as pressure, and the unit of pressure is Pascal. That's a SI unit of pressure. However, you can always kind of use pounds and square inches, so PSI. You can use them, but they're not SI units. So if you know the pound weight and if you know the area in square inches, you just divide pounds with the square inches, you'll get the PSI pressure. All right. In gases, what creates pressure is molecules coming and hitting. So if you have a surface and if molecules are kind of bouncing back and forth onto the surface, now each collision causes a force on the surface. When each of these collisions causes a force on the surface, you have a force, you have an area. So the molecular collisions is what causes the pressure from the gases. So in this room we have pressure. All right, so we call that atmospheric pressure. So the atmospheric pressure is measured by a barometer. So a barometer measures atmospheric pressure. Now you can have a pressure gauge. A pressure gauge is an instrument that actually measures the pressure difference between the atmosphere and the corresponding object. So if you're talking about a tire gauge, so a tire gauge is basically the pressure gauge. Now what does the tire gauge read? The tire gauge reads the difference between the inside and the outside. So if your tire gauge reads 32 and if the outside is 14 psi, then the inside must be 32 plus 14, which is 46. So what does the tire gauge read? The tire gauge reads 46 minus 14. That's what it reads. So if your tires go flat, the inside is going to be 14 and the outside is going to be 14. So it's 14 minus 14 is 0. So your gauge reads 0. So what will happen if you go to a place where the pressure outside is lower, like a mountain top? If the pressure outside is lower, then the difference between inside and outside becomes bigger. So your pressure gauge will read higher. So the pressure gauge is only an instrument that reads the pressure difference between the inside and the outside. Okay. Now coming to the next point. So in a liquid, if you take a liquid and if you have a solid inside the liquid, there is a pressure on the top, there's a pressure from below. Of course, as you go deeper into a liquid, the pressure is going to be higher. So this is a higher pressure and that's a smaller pressure. That causes a higher force from here and a smaller force from there. And that is what we call as a buoyant force. So what is buoyant force? It's a pressure, it's a force offered by the fluid on an object and the force is upward. That is called buoyant force. Now, Archimedes' principle tells you that when an object is fully inside or even partly inside, like that, if it is partly submerged or fully submerged, it is displacing a certain amount of fluid, and the amount of the weight of fluid displaced is the buoyant force. That's what Archimedes' principle tells you. So if anything is about floating objects like ships float, why? Because of Archimedes' principle. Because when something is floating, the buoyant force offered by this displaced fluid is what supports the entire weight of the object. So the buoyant force, Archimedes' principle tells you that the buoyant force is equal to the weight of the fluid displaced. Okay? And for a floating object, the weight of the fluid displaced, which is the buoyant force, is exactly the same as the weight of the object that is floating, like in a ship. Now, Pascal's principle is a principle that is applied in car brakes and stuff like that. So in hydraulics, this is completely the hydraulics principle. Pascal's principle is hydraulics principle. Okay, so what is the main idea of this one? You can actually transfer pressure from one place to another place, and thereby you can actually transfer forces, and not only transfer forces, you can magnify forces. So your car brakes and all that works on that principle. Then we have the Bernoulli's principle. Bernoulli's principle is what it says is wherever the fluid moves fast, the pressure goes down. Wherever the fluid goes fast, the pressure goes down. So we discussed in class a lot of examples about where the fluid can go fast and how it causes the pressure changes. Okay, so if you have a tube that goes like this, narrowing down, here the fluid is going to go slow, and here it's going to go fast. So wherever it's going fast, the pressure is small. Wherever it's going slow, the pressure is bigger. Okay, and we saw about an airplane wing. So if that is an airplane wing, when the air glides over the top, you can see there's a lot of squeezing effect on the top, and at the bottom not much. So therefore here, because the air layers are crowded, they go faster, big speed, and here smaller speed. And because of the big speed, the pressure is small here and the pressure is big here, so that's why you get the lift from here. So the pressure, the force exerted downward is smaller than the force exerted from here. So overall you get the plane wing supported, and what supports it is Bernoulli's principle. Bernoulli's principle is also used in multiple places. I told you about air fresheners, atomizer. So when you spray something, you are actually using the Bernoulli's principle. Okay. So those are things about that chapter. Then temperature and heat. Heat is the sum of the kinetic and potential energies of the particles in an object, whereas temperature is proportional to the average kinetic energy. Temperature is always proportional to the average kinetic energy of the particles. And temperature is measured in different units, Celsius, Fahrenheit and all that, but Kelvin is the unit which is SI. And now comes to temperature conversions. You should be in a position to convert temperatures from Celsius to Fahrenheit, or from Fahrenheit to Celsius, or from Celsius to Kelvin. You should be in a position to do this kind of a transfer change. So for example, if I tell you 40 degrees here, so what is 40 degrees Celsius? How do you convert it to Fahrenheit? So for conversions from 40 degrees to Fahrenheit, what you do is take 40, multiply it by 9/5, and then after you do all that, you add 32 to it. So 5 goes in 40, or you can do it on the calculator. 5 goes in 40, 8 times 9 is 72. 72 plus 32 gets you 104 degree Fahrenheit. So we are able to convert from Celsius to Fahrenheit. Now how do you convert from Fahrenheit to Celsius? You take the Fahrenheit temperature and then change it to Celsius. How do you do that? For example, if I have 104 degree Fahrenheit, what do you do? Subtract 32 from it, and then you multiply the whole thing with 9/5, 5/9, 5/9. So what do you do? Subtract these two and you get 72. So 72 times 5 over 9 gets you 40 degrees Celsius. Now to convert from Celsius to Kelvin, all you do is take the Celsius temperature, whatever it is, and then add it to 273, you get it in Kelvin. Okay, so that conversion is something that you definitely need to know. Now, coming to conduction, we discussed about conduction in class in detail. Conduction is when the heat energy is passed on from atom to atom. Convection is a bulk movement of matter, and the sea breeze and land breeze and all that is caused mainly by convection. Radiation is something that travels at the speed of light. So heat radiations, they travel at the speed of light because it's an electromagnetic wave. Okay, and in the chapter of heat, we did look into so many things about conduction, convection, and radiation. You should be reading it from your textbook as well. So make sure that you know all the stuff from the textbook. Now, bimetallic strip is something that is made up of two different materials, and they have different coefficients of linear expansion. So because of that, what happens is when you heat it, one expands more than the other, so it will tilt. So it will bend, and that bending effect is caused by the fact that they expand differently, and this is the thing that is used in thermostats and other things. All right. Then other things that you need to focus on, coming to waves, you should know what is a wave. Okay, it's energy propagation from one place to another place. What do you mean by frequency? Frequency is how many of these waves are actually passing through a certain spot in 1 second, or how many vibrations are taking place in 1 second. So when the particles bob up and down, how many times do they bob up and down in 1 second? So the unit of frequency is per second or hertz. Okay, and what is wavelength? Wavelength is the length from crest to crest, or trough to trough, or peak to peak, valley to valley. That's called wavelength. Or from all this is one wave. So that's one wave. You can say from here to here is one wave. The distance from here to here is called wavelength. Lambda is the unit for wavelength. Amplitude is the maximum height to which particles are tossed in a wave. So when a wave passes through a medium, when a wave passes through a medium, particles are tossed. So when the particles are tossed, they can go up, they vibrate up and down. So how far up do they go? And that is called, so the maximum displacement of the particles from the mean position. This is a mean position. So the maximum displacement of the particles from the mean position is what we call as amplitude. The very important equation is velocity is frequency times lambda. So if I give you the speed of waves, and if I tell you the frequency, you should be able to find the wavelength. Or if you're given the wavelength, and yes, for instance, if you are given the frequency, suppose the frequency is given as 5 kilohertz, and if you're given the speed as 300 meters per second. So how do you find the wavelength? So what you do is you use this equation. V is equal to F lambda. 300 is equal to 5 kilohertz. Kilo is 1,000. Mega will be a million. So 5,000 hertz times lambda. So to get lambda, what you do is you divide by 5,000. So lambda is 300 over 5,000. and that will be 3/50, which is 0.06 meters. So that's a wavelength. So that's how we calculate it. All right. and then of course, what is a transverse wave? A transverse wave is where the wave particles move up and down, but the wave goes forward like that. So waves on strings, guitar strings, waves on a rope, waves on water, they're all transverse. Longitudinal waves are sound waves. So sound waves are longitudinal because the particles vibrate parallel to the direction of motion of the wave. Okay, now what's a wavefront? Wavefront is when you start a disturbance somewhere, that disturbance is going to go all around. It's going to go all around. So at a certain time, the disturbance that was produced here must have gone to all these places. And after some more time, it must have gone to all these places. So these are called wave fronts. Now, which way the wave moves, we call it a ray, and they are going to be perpendicular. So now you can have circular waves, like these are circular waves. If you drop a stone into water, you get circular waves. Ripples are circular waves because it goes like now. What is a spherical wave? Spherical wave is when I'm talking and the energy is going in all directions in a three-dimensional manner. So if it is going in all dimensions, then that will be spherical. Otherwise, on water, it will be like circular. So plane waves. Now, what's a plane wave? When these circular waves, or when the spherical waves, when they literally go flat like this, when they go parallel to each other, these are called plane waves. Now, how can you get plane waves? When the source is kept very, very far away, they literally will be plane like that, flat. So when they are flat waves, now the wavelength is the distance between the two waves, and the energy is going this way. So this is how the propagation takes place, and this is a wavefront. So these are wavefronts, and this is the ray direction. Okay, so these are parallel and flat. That's wavefront. Now, what is diffraction? Diffraction is when waves pass through a gap. When waves pass through a gap, it starts spreading. So nothing happens to the waves, wavelength or frequency or speed. Everything stays the same. It's just that it spreads. Okay. So the wavelength here is the same as the wavelength here. The frequency here is the same as the frequency here. Interference. When you have two or more waves coming from two spots, like if you have two sources and waves are coming from here and from here, at these points they interfere. And when they interfere, they cause, in sound, they cause loudness and softness. In light, they cause brightness and darkness. So on ripples, you can see on water, if you have two sources like that next to each other, you will see water piling up at some spots and then kind of canceling each other's effect at some other spot. Those kind of things are called interference. So when waves meet, when two or more waves meet together, that causes interference. Okay. Now, Doppler effect. Doppler effect is when the source or the observer moves relative to the other. Then the frequency changes, or the pitch changes. The change of pitch is called Doppler effect. Okay? The change of pitch is called Doppler effect. So when an ambulance is turning on the siren and is moving towards you, if it is moving towards you, you will hear a higher pitch. So towards, high pitch. If it's going away, lower pitch. Now pitch means frequency. Now if it is a higher pitch, then the wavelength must be small. If it's a lower pitch, low frequency means big wavelength. Because wavelength and frequency, they go inverse proportion. When the wavelength goes up, frequency goes down. Okay? When the frequency goes up, the wavelength should go down. So wavelength is the distance between the waves. So when the frequency is small, now that is small frequency. The wavelength is big. Now this is high frequency. Now you can see the wavelength is small. So high frequency, wavelength is small. Low frequency, wavelength is big. So Doppler effect is in radar guns and all those. Doppler effect is used. Okay. Echo. Echo is a reflection of sound. Now when sound goes from here, goes all the way here, bounces off, and then returns back. If the time taken is for the entire trip, then you have to consider the total distance to be going forward and backward. Right? So if I say that the sound was going at a speed of 340 meters per second and it went and came back taking 8 seconds. It went and came back taking total of 8 seconds. What is the distance from this place to the reflecting surface? How do you do it? So you have the speed, you have the time. Speed is distance over time, or distance is speed times time. So you're given the speed 340 and you're given the time 8. So that gives you 2720, right? 2720 meters. Now remember, this 2720 meters is the distance going and coming. So the distance from here to here will be half of that, 2720 divided by 2, which is 1360. Okay, meters. Hope these things are clear so far. And so that is echo. Sound, you know there are 3 types of sound: infrasound, audible sound, ultrasound. They all go at the same speeds. The only thing is frequency. This one has got low frequencies, only up to 20 Hertz. This goes from 20 Hertz to 20,000 Hertz. And this is anything about 20,000 Hertz. That's ultrasound. But they all go with the same speeds in air. Okay. But then this one has got a higher frequency. Now ultrasound is used for multiple purposes. You should look into the textbook and find out what are the uses of ultrasound. The textbook. Look up ultrasound in the textbook for what uses they are put into. Infrasound is not of any big significant use. Only some animals use them. Giraffes, elephants supposedly communicate with each other with infrasonic frequencies. So infrasonic sound, ultrasonic sound, and audible sound. So this is pretty much what you need to know. All right, so all the best to you and good luck with this exam and with whatever you intend to do in future. All right, take care.